Hi, and welcome back to Codex. Our speaker today is Alexandra Kolla from UC Santa Cruz. Alexandra's research is spectral graph theory, algorithms, complexity, statistical physics, convex programming, and quantum computing. Today, she'll tell us about quantum max cuts and local Hamiltonians. Take it away, Alexandra.
Thanks for inviting me. It's been a minute since I gave a Zoom talk, to be honest. So we've moved back to in person mostly, I think. So it's I hope this works out. My internet is great, so I think yeah, it shouldn't be any issues. That's why I didn't go to the office because my office internet is really bad. I had to like stay at home for this. Yeah, so this is kind of like combining quantum, spectral, maybe statistical physics, depending on how you want to see it, and convex optimization. So it's like touching upon most of the areas of research. And my goal for today is mostly to motivate the problem, what it is, why is it important, and what does one do about solving it, rather than give you like super technical details on the proofs of the main theorems, which I will touch upon at the end. But I think my main focus would be why are quantum cuts cool, I guess, and hopefully, it would be if you their papers that we have out with my students mostly about this and another more general version. All right, so let's see. Okay, now I can't wait. Oh, there it is. So I will, in this talk, introduce what the question is, what are quantum cuts? I'm not going to go into what are qubits and qubits much, but if you do not know, feel free to ask me. Anytime interrupt me and feel free to ask me anything that I'm not covering. I assume people know what a qubit is, but I'm happy to explain in general. So this is what we're going to talk about. First of all, motivation from the classical world, what we call constraint satisfaction problems. In the forefront of constraint satisfaction problems that are key, typically NP-hard questions to ask in complexity theory are max cut and max d cut. So we're going to talk about those. And then we're going to talk about quantum constraint satisfaction problems. How do those relate to classical ones and what they are? The other term for quantum constraint satisfaction problems are local Hamiltonians, for those of you who do some quantum. In particular, we're going to focus on quantum max cut and quantum max d cut. And at the end, talk about our results, methods, and some future directions. So this is the plan. Again, feel free to interrupt at any point and ask any questions. So there we go. Constraint satisfaction problems. Let's just focus on a very key question in computer science, the max cut problem, that is asking on input a graph G with some vertices and edges. We want to partition G so as to maximize the number of edges being cut. And in this particular example, I have drawn the graph is bipartite. So the max cut happens to be all the edges because you can always partition into parts as to maximize all the edges cross. And this problem is important for chemistry, physics, and other areas. So like people want to find them, including computer science, of course, find the max cut problem. Unfortunately, it's one of the classic NP-hard proofs was that max cut is NP complete. So there is no hope to find algorithms to solve this problem that are efficient. Unless you believe that P is equal to NP, which people don't. So the next best thing you can do is approximate max cut. And sometimes for especially most applications in computer science, a factor of something approximation is fine. So maybe if I can approximate within a factor of 2, my algorithm would be good enough. Or a factor of maybe like, I don't know, 1 point. Some other applications need some more sensitive approximation guarantees. And there have been approximation algorithms for max cut. The most folklore trivial of which is a random cut. I flip a coin for its vertex and I put it in S or S prime with probability 1/2. And in expectation, also with high probability, this cut That's about half of the optimal. So there is indeed a factor of 2 approximation, or a half, depending on how you want to see the factor of max cut. There's also a convex optimization, namely STP, semi-definite programming approximation. 20 years later, basically, than the NP hardness result came about, that gives a better than a half factor. It gives a 0.878, so closer to 1. 1 is ideal, 1 is finding the max cut. And this is a very simple but also sophisticated, clever algorithm due to Gemons and Williamson that has the approximation ratio be a minimum over a trigonometric function that comes from the algorithm. And then, you know, of course, you want to push it closer to 1. How well can we approximate max cut? Is this the best algorithm? It kind of seems an unnatural stopping point. It kind of seems unnatural to think like 0.878 all of a sudden is the optimal approximation algorithm for max cut. I mean, a half would be more reasonable as like a nice round number. So you can ask, is this the best we can do? And it turns out if a key assumption in complexity theory called the unique games conjecture is true, then this is the best we can do. And I want to spend a few seconds saying something about the unique games conjecture, which is very little relevance to what I'm going to talk about next, but I think it's cool to know if you haven't seen this before. The assumption that P is not equal to NP gives us a way to argue that a lot of problems cannot have efficient algorithms. The assumption that the unique games problem is hard, meaning unique games conjecture is true, give us the tools to argue that a lot of these NP-hard problems are also hard to approximate. And it usually gives exacting approximability results. In this example, we know an algorithm that achieves in polynomial time a 0.878 approximation for max cut. And if this conjecture is true, this is tight, meaning it's NP-hard to do anything better. And this is not a coincidence. Unique games conjecture gives this landscape of inapproximability, exact inapproximability, for a lot of problems. So it's a cool complexity theoretic assumption to have as a step down from P versus NP. So that's all I want to say about this. So this is the max cut. It's been well studied and a lot of things are known. Now, what about quantum? In the quantum setting, we can generalize. So max cut is called a constraint satisfaction. It falls into an umbrella of a class of problems that are called constraint satisfaction problems, or CSPs. And if we look at this, you can see this as every edge needs to satisfy the constraint that the endpoints are assigned different colors or different, 1 minus 1 or different numbers, depending on how you want to see it. So max cut, it has a set of constraints, 1 per edge. The constraint per edge is that they're opposite values or opposite colors. So you want to satisfy as many constraints as possible. So it's a constraint satisfaction problem that asks for the maximum number of constraints to be satisfied simultaneously. So that's what CSPs means. Max cut is a key example of those. In the quantum setting, there is a thing called quantum CSPs. And this also goes by the name, the K-local Hamiltonian problem. What is this? So one is given an input that's exponentially large in the number of qubits, Hermitian matrix. This is known as the local Hamiltonian. And the important, clearly all quantum evolution, anything you do is a unitary, is given by a large exponential in the number of qubits matrix. But the cool thing about this setting is that it's a local Hamiltonian, which means it has a succinct description in terms of local quantum clauses. And I'll explain what that is momentarily. So the goal of this problem, the question asked, is to estimate the smallest eigenvalue or largest eigenvalue. They're both equivalent complexity-wise in most cases, which we also in physics call the ground state energy of this Hamiltonian. So here's what a K-local Hamiltonian is. It's a matrix H that is given as the sum of local terms H of S. And while H acts on all the qubits potentially, its H of S acts on a constant number K of fixed, I guess, it need not be constant, of qubits denoted by some subset of the qubits. And the constraint is that this number of qubits, the set S, has always cardinality equal to K. So here's an example of a two-local Hamiltonian. Assume you have 4 qubits, one given per line, and then I have a two-local Hamiltonian. So these black dots are basically, can you see my cursor in the share screen?
Yes.
Like when I move this, okay. So yeah, this thing represents one of those terms where K equals 2, and this matrix acts on only 2 qubits, and here, and here, and here, so on. So this is you can sum all of those up, and this is a two-local Hamiltonian that acts on 4 qubits. So the nice thing about this local Hamiltonian is that each of those terms is a 2 to the K by 2 to the K matrix. And the best way to think of K is some constant, like 2, 3, 4. So it is actually a constant size matrix, which means typically it would be hard to write down 2 to the n by 2 to the n general Hamiltonian, but now it's easy because all I have to do is specify these local terms that are constant size matrices. And informally, okay, there's like a technicality because all the H sub S's need to have the same dimension as H. So you just append the identity, tensor it with the identity on everything else. So the dimensions match, this is not an issue. So why is this even, so far it seems a completely unrelated definition. I said, okay, we have matrices given by sum of local matrices, and we want to find the ground state, the minimum, maximum eigenvalue or eigenvector. Why is this a quantum CSP? Like why is this even relevant? Well, it turns out, and it's not very hard to see, we'll do an example later, that if these matrices, and sorry, the subscript has not showed up here for H sub S, are diagonal, then this is exactly a classical CSP. In particular, we will show how maxcat can be phrased as finding the maximum eigenvector of a local Hamiltonian where all the terms happen to be exactly diagonal. So this is the direct generalization. You can see classical CSPs as finding ground states of Hamiltonians where H sub S's happen to be diagonal. Generalizing this to general matrices that are not diagonal is a quantum CSP. I think I saw something on the chat, but I'm not sure if there are any questions so far.
You're good.
Okay. So this problem has been important, multi-way important in many aspects of science. It's important to physics because this is a problem of estimating the energy of quantum many-body system when cooled to near absolute zero, the ground states of those systems. It's important to complexity theory because local Hamiltonian finding this ground state is the first known what we call QMA, quantum Merlin-Arthur complete problem, where this is the quantum analog of NP. So if one day quantum computers are built, now that we have classical computers, clearly we're asking what can be computed efficiently, and whatever is NP-hard is not believed to have efficient algorithms. If we had quantum computers commercially available, whatever problems are QMA-hard, we won't hope to have efficient quantum algorithms. So it's the analog of NP for quantum computers. And it's a central problem to study in the field of quantum Hamiltonian complexity. That's a field on its own. And it uses tools from complexity theory that uncover limits and structure of actual physical systems in nature. And this is basically what whole of quantum computing is. It's a way to teach quantum physics via, I want to call it linear algebra, but let's call it computing. in my opinion. This is the whole benefit, I guess, since commercial quantum computers seem a little far-fetched. Quantum computing is important still because it teaches quantum physics without physics, which is pretty cool. All right, so first of all, why is this problem hard? Because we talked about computing eigenvectors of minimum or maximum eigenvalue, and this is not a hard problem. There's a polynomial time algorithm to compute eigenvectors, all the eigenvectors, in fact, of matrices. However, as I've noted before, H, this big matrix, is a 2 to the n by 2 to the n dimensional matrix. So generally speaking, an eigenvector that would be a ground state would be an exponentially large vector. And, you know, we have no way, unless that we know of, unless we have exponential time, which is inefficient, to run the standard eigenvector and eigenvalue algorithm and come up with this. So we want something polynomial time, not a scaling with a dimension of this matrix. So that comes in handy that the Hamiltonian is local, because as I said, at least the input has a succinct description. So the input you can feed to the algorithm in polynomial time by just feeding those local terms. And they're typically polynomially, many of them that are in the most key applications. So any algorithm that takes input this local Hamiltonian and tries to compute the minimum or maximum eigenvector or eigenvalue, it also needs to output a succinct eigenvector, you know, a description of a solution that's reasonably succinct. This is called an ansatz. Here's an example. So an example would be the algorithm outputs a n-qubit product state. And product state is kind of like, if you're not into quantum, it's a quantum analog of a product distribution. You know, generally distributions of n random variables could be super complicated, but if each of them is independent, then their distribution is just a product distribution and super easy to turn off bounds or whatever else you want to do. Similarly, quantum states, a product distribution is specified by tensor product of states for each of those qubits. So it can be described in some polynomial time in n, which n is the number of qubits. So it's polynomial description. Even though product states are not entangled, so they have an easy description as quantum states, they immediately generalize classical bit string assignments. So at the very minimum, we argued diagonal local Hamiltonians are quantum classical CSPs. So finding product states that maximize or minimize eigenvalues of those is already NP-hard, because we know CSP maximization is NP-hard. So already this problem is very hard in the very simple diagonal case. Okay, so right, so this problem is hard basically, and we want to see what we can do about it. Hopefully I've convinced you so far that it's interesting to look at for many reasons, and that there is some difficulty in approximating those problems. So let's see the specific interesting cases that we deal with in this work. All right, so this specific local Hamiltonian we're going to talk about is called the quantum Heisenberg model. It has its own name because it's been well studied in the theory of magnetism in physics, which I know nothing about, so I hope nobody asks me. I'm not a physicist and never had dabbled in physics for any reason whatsoever. I love physics, but it's very hard. And not only that, is a direct generalization of the classical Max-Cut problem we've seen. And what is it? It's a family of two local Hamiltonians. So it acts on each term acts on two qubits. Constraints are hij acting on qubits I and j. And this local term, each local term is given by this matrix, which is a 4x4 matrix. And then I append tensor with the identity, as I said, that the x, y's, and z's are the standard Pauli matrices. I'll say what they are exactly, but they're pretty well studied in quantum in physics in general. Alpha, beta, and gamma are just parameters that we will tweak to define different problems. I is the identity, and xi indicates that x acts on the qubit I. So that's what this means. So here's the term. There are three cases that I'm going to talk about, and they're important, and I'm going to talk about in this. The first one is the actual max-cut problem. Remember I said every CSP can be written as a Hamiltonian, a local Hamiltonian, where diagonal, the HS's are diagonals. In this case, when alpha is equal to beta is equal to 0, and gamma is 1, this becomes I minus Zi tensor Zj. Z is a diagonal matrix. So this is exactly finding the maximum eigenvalue of this Hamiltonian is exactly the max-cut problem. Second interesting is the antiferromagnetic, what we call XY model, where alpha beta is 1 and gamma is 0. Important to physics, haven't studied it so much for quantum computing and computer science. And the more general case, the antiferromagnetic Heisenberg model, which is going to be the focus of our talk, or quantum max-cut, is where everything is 1. So a cool thing, I don't know if it's cool, but I find it cool. The quantum max-cut, which is this case, is notoriously difficult to solve even on bipartite graphs. This is in contrast to classical max-cut, because we know that for bipartite graphs, classical max-cut becomes super easy. You just cut all the edges because you can find the bipartition in polynomial time. So all of these problems are just way harder than classical problems already. But let's see, first of all, as a warm-up, why is this case actually the classical max-cut? All right, so this is the Z matrix. The Z Pauli matrix is diagonal with 1 and minus 1 in the diagonals. Again, append the identity for the correct dimensions. So it's diagonal in the standard basis. Standard basis is just the delta function basis, with eigenvalues 1 for eigenvector 0, and 0 just means it's a, I don't have my tablet, but it's like the 2D vector that has 1 and 0. And this ket 1 is the 2D vector that has 0 and 1. So they're the two basis vectors in C2, the complex, C by C. Does it make sense? Sorry, I can't write down, but basically those are the two-dimensional basis vectors. And Z is diagonal in those. Clearly, they're both eigenvectors with eigenvalue 1 and minus 1. So Z tensor Z, which is our local term now, is also diagonal in the standard basis, and the eigenvectors are just the tensor products of these two. And there are 4 possible ways to tensor product ket 0 and ket 1. And by the properties of tensor products, these two 0, 0, and 1, 1 have eigenvalue 1, and 0, 1, and 1, 0 have eigenvalue minus 1. So now identity minus this has eigenvalues either 0 or 2. Identity, everything is an eigenvector. So in particular, those 4 are the eigenvectors of this big matrix. And identity minus, so our local term has eigenvalues 0 with a 0, 0, 1, 1 eigenvectors, and 2 with a 0, 1, 1, 0 eigenvectors. What does that mean? So Hij, we have an underlying graph in mind, and we think of Ij as being the edges of the graph. So in our big Hamiltonian, we add a term Hij per edge of the graph. So now for this big Hamiltonian, it's a sum of these local terms. And we can note for every edge Ij, the 0, 0, and 1, 1 eigenvectors contribute 0 inner product, and the 0, 1, 0, and 1, 0 eigenvectors contribute a 2 inner product. What does that mean? If 2 qubits that are connected by an edge are set to opposing standard bases, 0, 1, or 1, 0, then we obtain a value 2 from the quantum constraint on this edge. And if the qubits are set to identical standard bases, 0, 0, or 1, 1, we obtain a value 0. So that starts to sound a lot like cutting. If you put them on the same side, this term doesn't contribute anything. If you put them on opposite sides, this term contributes 2. So since all the local terms are diagonal in the standard basis, the entire big Hamiltonian, which is the sum of those terms, will also be diagonal in the standard basis. And the largest eigenvalue would just be the sum of values obtained on each edge by the best standard basis state. This is exactly the maximum cut in the graph, because you're trying to maximize how many of these terms can give you a value 2. So a max cut corresponds exactly to an assignment of 0 ones to the vertices, to the qubits. And this vector, the 0, 1, 0, 0, 1, whatever ket, gives you a value that's twice the max cut problem. So max cut and maximum eigenvector / eigenvalue of this Hamiltonian are equivalent. You can phrase it as a constraint satisfaction problem, as a maximum eigenvalue of the sum of these local terms. And the maximum eigenvector is exactly the maximum cut assignment for the constraint satisfaction problem. Any questions so far? All right. There is yet another way to see this that's going to be useful when we generalize to the quantum computing world. So seen as now a 2 local Hamiltonian problem, that's what I mean by 2LH, the classical max cut problem has an edge interaction, which is meaning this matrix I minus Zi tensor Zj can be written as the sum of these 2 projectors. These project to the opposite states, basically. So I can write this matrix as identity minus the tensor of the Paulis, or I can write it as 2 times this projector onto this, what we call antisymmetric space. This is just like a very simple calculation. And for those who don't know the bracket notation, this is outer product. So these 2 are rank 1 matrices that are given by the outer product of this vector and this vector. Okay, so this is classical max cut. We completely phrase classical max cut as a local Hamiltonian question, 2 local Hamiltonian. We discussed that the solution, the optimal solution to max cut is the maximum eigenvector, and the maximum eigenvalue is the max cut. Well, we have to scale by half, but let's forget about the factor of 2. That's easy to do. Right, and then we phrase the max cut as yet another way to write it, which is the projection onto the antisymmetric space on these 2 qubits. All right, so now let's go to case 3, which we call the quantum max cut or the Heisenberg model, where these 3 Paulis all exist in the local term. So that's no longer diagonal anymore, only Z is diagonal. So now we have a local term 4x4 matrix that is something, but it's not diagonal. So before, we had a payoff function where the payoff was 2 if the 2 assignments of the qubits were different. If the 0, 1 or 1, 0, we got a 2 in this payoff function. So now this notion is replaced by the energy of 2 local subsystems of qubits, again on the projector onto the antisymmetric space, which for 2 qubits is the projection onto this Bell state, the maximally entangled Bell state. So again, its vertex is a qubit. To its edge, we have a local Hamiltonian term that looks like this, with alpha, beta, and gamma equal to 1. And just like we did for max cut, that we projected on, we wrote this down as the sum of the projectors onto these 2 values that give us non-zero payoff in the maximum eigenvalue. We can write this down as well as a projection onto this maximally entangled Bell state. goes by the name of Y minus typically in literature. So this is also an easy calculation to see that this is the outer product. So what is known for quantum max cut in terms of algorithms? There's a STP-based algorithm by Briette and Oliveira Filho and Valentin that gives a polynomial time approximation scheme that approximates by 0.956 to the optimal product state solution. Remember, now we have an extra challenge. When we're asking of finding maximum eigenvectors and eigenvalues of local Hamiltonians, we need a succinct way, an ansatz, to represent even our solutions. So we can't just output the best arbitrary quantum state, because this could potentially have an exponentially large description. So if we restrict to product states are only going to be an approximation. So the optimum over product state is only going to be an approximation at best of the optimum over all states. But what they do is they give a 0.956 to the optimal product state solution. And there is a way to kind of get a 0.498 to the best possibly entangled state approximation that's way more complicated than just doing product states. So this is algorithmically what's known. Complexity theory wise, it is QMA-hard to compute exactly. And not only that, there's a what we call integrality gap for the basic STP that the previous people used for the algorithm. And it means you cannot achieve the optimal approximation ratio with this technique. Not only this, but we go back to this unique games business that somehow rears its head not only in the classical inapproximability world, but also in the quantum inapproximability world. That shows that it's unique games hard to compute a better than 0.956 approximation of the value of the best product state. And this was the algorithm that I just mentioned. So there exists an algorithm that achieves this approximation to the product state, and it's unique games hard to do better. So these problems seem like tightly related, quantum max cut and classical max cut, not only because one is a direct generalization of the other, but also because complexity theory-wise, they're similar tools to understand how hard they are. And also is a hard to compute the 0.956 plus epsilon approximation to the optimal possible and possibly entangled, most likely entangled state.
Excuse me, I had a question.
Yeah.
Can you quickly say what you mean by the non-commutative sum of squares?
Oh, it's just like a way to write a semi-definite programming. So basically, it's a very long answer where you start with a basic semi-definite program and then you add constraints to it in a way that every class of constraints you add gives you a solution that's closer and closer to the actual optimum. And I'll write down the STP later on in this talk to give you an exact example of what that means. So there's a positive semi-definite constraint. It's an STP, so we have PSD constraints. And there's a way to write this as a sum of squares kind of like requirement of our constraints. I know this is not answering the question exactly, but there's a big, how do I describe this best? Maybe like ask me again when you see the STP.
Yeah, sure, yeah. Thank you.
Okay, yeah. All right, so I want to quickly mention another interesting case which goes in physics by the name EPR Hamiltonian, which is the projection onto this other Bell state. Instead of a minus, we have a plus, and also can be written as not all minuses, but we have plus x tensor x and plus z tensor z. There's no hardness result known for this, so for all we know. It may not be QMA-hard. It is possible that we can solve the optimal state in polynomial time. Why I'm mentioning this is because I'm really interested in the question of bipartite quantum max cut. Because bipartite classical cut is very easy, what about bipartite quantum max cut? So for a bipartite graph, it turns out the EPR problem and the quantum max cut problem are equivalent because we can transform the EPR Hamiltonian to the quantum max cut Hamiltonian just by rotating the qubits in one of the partitions by the Pauli matrix Y. So this holds, and Gij are the local terms for this EPR, Hij were the previous local terms for the Hamiltonian. So solving anything, any algorithm for EPR automatically gives you an algorithm for quantum max cut on bipartite graphs, which would be super cool because we know nothing about bipartite graphs on max cut unless the graphs have specific structure. This is one of the questions I am very interested in, but seems very hard to tackle, at least with what we know. Also note that any algorithm for either of those two Hamiltonians that searches only over product states cannot be better than a half approximation. Why? Consider an instance that's just an isolated edge. The maximum energy of a product state is 1, yet the entangled single state, meaning the Bell state, gives energy 2. So already at the edge, if I restrict myself to only finding product state approximations, a half is my bound. I cannot do better than a half. So it's kind of like doomed from the beginning, but product states are pretty to describe. So we still have a lot of focus on product states. And yeah, there's a matching algorithm for quantum max cut for a half. Okay, so I guess I have set up the landscape as to what type of questions quantum CSPs are looking at and why they are interesting / important / hard. So what do we do? And we have a line of work. This is the oldest of the two papers we have, but it's, I guess, more suited for a talk, and it gives most of the important intuition about what's happening and why things are important. So what we do in this work, we generalize the two local Hamiltonian problems to Q-dits. So what are Q-dits? Well, Q-bits are the equivalent, the quantum bit. So they're in a superposition of 0 or 1. Q-dits are, again, single particle states that can take one of the values. So it would be the state of a Q-dit would be a superposition of 0, 1, 2, 3, k minus 1. So what we do in this work is we generalize the two local Hamiltonian problems to Q-dits. We need to define the model, design algorithms with non-trivial guarantees, and ideally have matching hardness. Now, why Q-dits? Let's go back to the classical constraint satisfaction problems. And let's look at a problem that is called the max D cut. Okay, we had max cut. We want to partition in two pieces that maximize the number of edges cut. But typically in computer science applications, a lot of times we're faced with some clustering, some communities that appear as different clusters, and we want to kind of partition more than two parts of the graph to maximize the number of edges going across. So max D cut does exactly that. It acts to partition the vertices into D sets that maximize the number of edges going across sets. And in this specific example, there are 3 partitions that maximize the edges. Green and red are just a single vertex, and everything else is blue. And there's a simple randomized algorithm for max D cut that results in a 1 minus 1 over D approximation, and also a better bound by Fries and Jerome, who extend the Gemans-Williamson max cut algorithm to an algorithm with additive improvement log D over D squared. And we have like a lot of other, there's a lot of work also on max DCAT because of its importance to community detection and partition and all of that stuff in computer science. Similarly to max CAT, we can write max DCAT is a classical constraint satisfaction problem. We can write it as a two local Hamiltonian problem. And the best way to understand this is via this edge interaction, the projections method. And the projector, each local projector is just the sum of the projections onto the antisymmetric space where it gets different values, A and B. So if our alphabet size was 3, it would be 0, 1, 0, 2, 2, 3, the sum of all of those projectors. So here is max DCAT, and what we do is to generalize DCAT to the quantum max DCAT. And similarly to quantum max CAT, this can be seen as replacing the D-colors with D-dimensional Q-dits and replacing the payoff, which was the projection to the different values basis, to the projection to the antisymmetric space, which is just the sum of those maximally entangled, let's call them generalized Bell states. It's a rank D choose to projector onto these states. So here is how, in math, our local Hamiltonian terms look like. It's just the sum of the outer product. I need a transpose here. A transpose here. No, sorry, it's a bracket. I don't need anything. This is good. This antisymmetric space. It turns out that just like max CAT, you can write it as the sum of these Pauli tensor products and also as the sum of the projectors. There is an expression for this local term as a sum of some matrices. It's called the SUD Heisenberg model. This is also well studied in physics. And those lambdas are the generalized Gell-Mann matrices that are higher dimensional extensions of the Paulis. So this is quantum max DCAT expressed, their local terms of quantum max DCAT expressed both as projectors and as sums of matrices. Okay, so what we want to find again, and I didn't do this thought experiment for max DCAT, where is it? Here. But it's not hard to show that for these local Hamiltonians, the basis vector that achieves the maximum classical DCAT would be the eigenvector of maximum eigenvalue for the Hamiltonian, again, just like the max CAT. So now for the DCAT, we want to do the same. We want to find lambda max of this Hamiltonian, which is the sum of the local terms, which is the max over all vectors in the large dimensional, exponentially dimensional space, d to the n, unit vectors of this inner product. You can write this as the maximum over trace over density matrices. Density matrices represent generally mixed quantum states of rho times h of g. So this is a standard way to transform one quantity to another. Okay, so our results are summarized in this slide, and I guess I have only little time, so I'll go quickly on what that is. So basically, we get a non-trivial performance guarantee bigger than a half 1 minus 1 over d. Remember, a half is the bound over product states, so we cannot do better than a half. So we do close to a half. And there are like some more results along those lines for specific cases or an improvement of this. So we present the SDP algorithm that achieves a non-trivial performance guarantee. And this is non-trivial because the maximally mixed state, which would be the equivalent of a randomized algorithm, achieves a half. So it does better. Okay, so here is the SDP. And what, generally speaking, these STPs do, we want to, again, maximize the trace over mixed states times HUV. but we cannot impose the constraint that rho is a general quantum state. That's our issue, because general quantum states have exponentially large descriptions. So we cannot write a polynomial size STP that imposes this constraint. So what we want to do is impose some constraints that general quantum states satisfy, but they're also computable in polynomial time. So these constraints happen to be those, which I don't want to get into detail as to what they are, but I do want to say that what happens in any semi-definite program is that it outputs some matrix. Here it will output some matrix rho that satisfies these things that say something about partial traces. So rho is like a pseudo density matrix in this setting. It may not be a full density matrix, because if it is, then we solve the problem exactly. So my STP outputs some matrix rho that needs to be positive semi-definite because it's an STP. So we can see this matrix rho as having vectors per vertex, and this is the gram decomposition of the matrix rho. Each ij entry of the matrix rho is an inner product of two vectors, ui and uj. This is a standard back and forth between matrices, PSD matrices and vectors. So we can consider this STP as giving us, spitting out, a vector per vertex that belongs to some dimension space, which we'll talk about in a second. So now our solution to this STP just spits out a bunch of vectors. All right. What do we want to do? Ideally, from this collection of vectors, we want to find a product state, meaning a qdit per vertex, tensor product with each other, that gives some reasonable approximation of the optimal value. How do we do that? We take those vectors u that the STP outputs. We select a random Gaussian matrix Z. Every entry is a random independent Gaussian. And we output this vector B sub u, that's some scaling, times the projection Z, times the, Z u. So we can like project my u into a random Gaussian matrix and output the result. Right, so this is the full algorithm, basically, but there are some complications. Before I talk about these complications, let me know if it's kind of clear what, even though it's completely not clear why this algorithm would work, at least is it clear what the algorithm is? All right, so now let's talk about why this algorithm makes, the results of the algorithm make sense. So as I said, the equivalent of a randomized rounding, meaning how we did for max cut, we assigned a random cut and it achieved a half of the optimum. The equivalent of this would be a maximally mixed state. Energy of the maximally mixed state, it would be no worse, the value of the quantum max cut Hamiltonian on this would be no worse than a half 1 minus d times the optimal. So our theorem says that at least our algorithm is non-trivial because it's better than optimum. The completely random solution. Note that when d equals 2, this is quantum max cut. So this is just a direct generalization of the stuff I talked about before with a quantum max cut. So now, why is this algorithm challenging? So here is the main challenge, and I don't have much time, so I want to. There's a challenge that the matrices we're dealing with are no longer unitary, unlike the Pauli's. But the main challenge is with our vectors. Because let's go back to the algorithm and see what we're doing. The STP spits out a vector, and we do some randomized rounding of this vector to find a product state. meaning to find a qubit per vertex. If D was 2, meaning if those were qubits, vectors in the sphere and quantum states are equivalent. So for those of you who know quantum physics or computing, every quantum state is a point in the what we call Bloch sphere. So it will be enough, and it has been enough in the max cut line of work to find vectors that have some good optimal value here. And those vectors immediately correspond to qubits. So it immediately correspond to product state solution. However, this is not the case here. So the notion of Bloch sphere does not exist for qubits when D is bigger than or equal to 3. So we cannot just round to the unit sphere for the Bloch vectors of pure states. So we need to do something else. We cannot just get the vectors of the SDP and say, okay, those are pure state vectors that correspond to product state solutions. And so this was one of the main challenges we had to overcome. And this is a picture of how we overcome this challenge. So we basically, instead of immediately associating every vector with a quantum state, we round to a Bloch vector on what we call the in-sphere. So there's a way to take this set of solutions and restrict it to something that actually corresponds to Bloch vectors by doing some quantum topology that other people have done for us. Yeah, so this is basically the main challenge. And if you want to see the details on exactly what the in-sphere and out-sphere is, they're on this slide. But I think since I don't have enough time to exactly explain what's happening, it's better to skip ahead, and I'll probably post the slides, and the paper is also online, and talk about a couple of future goals that I wanted to look at in case anybody is motivated. So it turns out if the graphs are dense, optimal states are very close to product states. So you might as well restrict to product states in your approximations. So sparse graphs seem to be the hard instances for quantum max cut and quantum max d cut. So we wanted to look at expander graphs, where expander graphs are basically the best approximations of the complete graph that have constant degree. They're sparse graphs. You can also see them as graphs that don't have very sparse cuts. You can also see them as graphs that lambda 2 of the Laplacian is large, is not close to 0. So what we wanted to do, and that seems a little hard at this point after we looked at a few math, but if someone has any intuitions, I don't know, is to extend the fact that for expander graphs, potentially product states are close to optimal approximations of general ground state for max cut and max d cut, quantum max cut, and generally do the same for sparsifiers of dense graphs. What is the relationship between the spectral profile of the graph and how well it approximates a dense graph spectrally, as opposed to the quantum solutions of these local Hamiltonians, and of course find what are the hard cases and better approximation algorithms, as well as matching hardness. I guess I'll stop here because it's about an hour, so I don't want to take up too much time, but if you have any questions, feel free to ask.
All right, thank you very much. Let's thank the speaker by smashing one of those reaction buttons. And